Okay, hello everybody. So I'm very pleased to give this conference on the Metamaterials. So just to inform you, this is a conference which will give you some aspect of some research project. Okay, so it's not really a tutorial. It's just the idea is to show you the new type of materials that have been that people have started to work on since approximately the beginning of the 2000s. So it's a very recent area. So I just want to give a brief introduction on that, and then I will focus on some specificity of the work I'm doing. The work I'm doing with the people in France. So this is a work that involves several people, which are some people who do acoustics, like this colleague here and this colleague here, and some people who do formulation and fabrication of materials. Okay, but I will more focus on the more on the fabrication aspects. Okay, so the title of my talk is Acoustic Metamaterials. So of course I will start by explaining what is a metamaterial. So meta means beyond. Okay, and so what is the definition of a metamaterial? It is a material which is structured, micro or nanostructure, and in which the propagation of either acoustic or electromagnetic waves is not conventional. Okay, it is a strange material with respect to the propagation of waves. Okay. So the definition is an artificial material exhibiting non-usual either electromagnetic or acoustic properties. And the challenge of the people who are trying to work on metamaterials is to build a material where the values that control the propagation of the waves inside the materials can be tuned, can be controlled, can be changed with at a given values. Okay. So as I told you, there are two types of waves. Okay, so if we talk about electromagnetic waves, what drives the propagation of light inside a material is the value of what we call the dielectric permittivity and the magnetic permeability of the material. Okay. These two values are controlling the speed of propagation of these waves inside the material. And if we talk about acoustic waves are, so you know, electromagnetic waves are the propagation of an electric field and a magnetic field, okay? Whereas acoustic waves are made of propagation of pressure waves. Okay, so it means that in the material you have a modulation of the pressure, okay, with some space in the material which have a high pressure and some space in the material which have low pressure, okay? And of course this pressure difference are coupling with the density, the local density of the material, okay? So the propagation of sound, for example, is in air, is a modulation of the pressure in the air, and these pressure waves are traveling into the medium by modulation of the density. So for electromagnetic wave, the speed of propagation is the inverse of the square root of the dielectric constant and the magnetic permeability constant. Okay. For an acoustic wave, the acoustic speed, okay, is 1 over the square root of the effective density of the material. So this is a mass density, and what we call the isentropic compressibility of the material. Okay. So of course density, what it is the mass per unit volume. Okay. Compressibility is a response of the material to a change of pressure. Okay. If you apply a pressure to a material, you see the amount of variation of the volume that it produces inside the material. So there is a kind of equivalence between the dielectric constant for the electromagnetic wave, and the compressibility for the acoustic wave, and respectively for the magnetic permeability and the density of the material. Okay? So what do we mean by exotic values of these quantities? Okay, so exotic values, we can, now you all know what is an optical index. The optical index is the speed of light in vacuum divided by the speed of light in a given material. Okay, so you see this is the square root of a relative electric constant, dielectric constant, and the square root of the magnetic relative permeability. The same way we can define an optical index, we can define what we call the acoustic index, which should be the speed of variation of propagation of the sound into not the vacuum, because in vacuum the sound does not propagate because there's no there cannot be any modulation of the density, of course, but here in the air, divided by the speed of propagation of the wave inside a given material. And expression of the expression of the acoustic index, which is the square root of the relative effective density and the square root of the relative compressibility. Okay? So, what is the interest of making metamaterials? So, as I will tell you, what we call exotic values of the effective density and the compressibility are, for example, negative values of the effective density of the material. I know it sounds a bit strange, okay, to say we're going to do a material with a negative effective density, but I will explain what I mean by this negative value. And here, so if you are, and the same for the compressibility, okay? And one important about waves, so I'm talking about propagation at given frequencies, okay? We can vary the frequency of the acoustic wave, we can vary the frequency of the electromagnetic wave. So say we are making a material with a negative effective density or a negative effective compressibility. Then, from the formula I've just given before, the acoustic index will be, if we take the square root of a negative number, you have a complex number, okay? So if you have one of these two constants which are negative, it means that you will have a negative acoustic index. Situation, you set an acoustic wave, for example, at a given frequency omega star into the material, and if for this frequency the acoustic index is a complex number, it means that the wave material, the propagating wave that comes into the material, will not propagate inside the material, but will become an evanescent wave, okay, and will exponentially decrease as a function of the distance inside the material. So it means that it will not penetrate, virtually not penetrate the material. So with this type of material, you would be able to make very precise acoustic filters, because the wave coming with the omega star frequency will not penetrate the material, but the other could, for example. And you can make mirrors, you can make waveguides, etc., etc. If you take now a material able to make a double negative material, it means to achieve negative values of the effective density and isentropic compressibility, then you can have a negative refraction index. And I will show you what kind of application you can do with that, but I can just say that a negative refraction index, the other way around, this, if you have an evanescent wave coming into the material, then as it will penetrate the material with this negative acoustic index, it will become propagating wave. Okay. So now you may wonder, of course, what is a negative effective density? This is completely strange. We've never heard of that before. And to explain that, you have to know that a negative density material, what can be done is to put some inclusion in the materials. So that's where the nano will come in play, and that's where the structuration of the material will come into play in this problem. In fact, this will not be nano in that case, but it is a general for you that to give you the idea of what a negative effective density, for example, is. Okay, so imagine you have an inclusion like this. Okay, the small on the top left of the material, the small drawing. Okay, and you have an acoustic wave penetrating the material. Okay, an acoustic wave is a varying pressure field. Okay, so locally this varying pressure field will act as an oscillating force on the inclusion. It's just like if you had someone that would push the material in one direction, very strong, very slowly, very strong, very low, and so on. So if you do like this, it means that you will create a resonant frequency. You can have a resonance frequency at which the oscillation, the pressure wave, will be exactly at the same frequency as the incoming wave. Okay, so it means that the acoustic wave are vibrating in phase. Okay, so it means that the material is following the acoustic wave. Okay, so the acoustic wave is moving at a given frequency and the given phase, and the little inclusion is following the acoustic wave. Okay. Now, if you are just after, this will happen for a given value of the frequency, of the resonance frequency. If you are just after this resonance frequency, what happens is that the vibration of the inclusion, the oscillation of the inclusion, will become out of phase with the vibration, with the pressure wave. Okay? So it means that while the pressure wave would push the material, answered by a force in the other direction, by an acceleration in the other direction. So it means that you have a negative value of the effective density, because the effective density is a ratio of the acceleration on the inclusion divided by the force that is applied on the material. Okay? So having a negative effective density material is just having a material in which the acoustic wave will oscillate at a given frequency and a given phase phi, and the inclusion will oscillate at the same frequency, but with a phase opposition. Okay, with a phase, the oscillation of the material will be completely out of phase with the oscillation of the wave. Okay, so at this very frequency here, you will have a negative effective density of the inclusion. Okay? And you can have exactly the same with what we call the monopolar resonance. So this is what we call a dipolar resonance in the first case, because you have a motion of the center of gravity of the inclusion. Okay? Whereas in the second case, here, in the case down, which is a monopolar resonance, you don't have gravity center of the inclusion, but you have rather an oscillation of the volume of the particle of the inclusion. Okay, and this oscillation of the volume of the inclusion with the incoming wave, in the case of a negative compressibility material, is when the oscillation is out of phase with the incoming wave. Is that okay? So you see that this is not something like very magic or whatever. It is just a dynamic effect, and this will happen at a given frequency. So when we talk about metamaterials, of course, we talk about some meta properties at a given frequency. So and this is what is on this schematic here also. This oscillation of the pressure field gives rise to an oscillation of the inclusion, okay? And exactly the same when you have the oscillation of the pressure field, what happens is when the pressure is high, the material is expanding, and when the pressure is low, the material is collapsing, which is completely counterintuitive. Okay? So now, what would happen if we had a negative refraction index? You've all heard about what we call the Laplace law. Okay, Laplace of a wave at an interface between two medium with different. Okay. If you have a normal refractive index, I mean a positive refractive index, you have the situation which is depicted on the scheme that is at the top of the slide. Okay, and you will have a θ2 angle which will be smaller than a θ1 angle. And if you are with a metamaterial, what happens is you will have the situation that is depicted here on the bottom of this slide, and you will have what we call a negative refraction. Okay? So you can imagine that with such material, you would be able to make what we call a planar lens. Okay? A planar, you are able to focus, okay, with no curvature of the lens. In optical problem, usually the lens, the converging lens, are curved, okay, to ensure that the propagation of light can converge on one. Still working? Okay. Here with this type of system, you will have convergence of the waves, but with a planar lens like this. So you have of aberration and so on. Material with you can make a material with that would transform an evanescent wave into a propagating wave, which is very interesting for the sake of application like sub-microscopy at the sub-wavelength. So let's see what has been done on the structure material to get a negative effective density. The first work that has system is a work by Liu and co-worker in 2000, and they have done a cubic crystal which was made of oscillators, okay, inclusion. And this was made of lead balls, lead little balls like this, 1 centimeter diameter, which are embedded into a soft polymer shell, and this core shell system is embedded into a hard polymer matrix here. And when you apply the, oh, sorry, it's okay, sorry. And when you apply the acoustic field, you make an oscillation, you trigger an oscillation of this little bead here, okay? And you see that you have, if you look at the amplitude of the transmission coefficient, you see that you have indeed some frequency, some resonance phenomenon, because you have a kind of divergence of the, a kind of, a vanishing of the transmission as a function of the frequency. So it means that the wave is completely dissipated by the material, okay? So this is the first example of what would be a negative effective density material. Okay, another example is these people have been able to make a 1D crystal of resonator where the material is constituted of small cavities, and these cavities are able to resonate with an incoming sound wave. Okay, and the same for this, you have the presence of a resonating phenomena. Okay, another very clever application is this, you see, these people, they took a grid, and on this grid, they put a membrane, okay, like a tissue membrane, and on this, on any single square here, they put a little weight, a very little weight, and because of the size of the rigidity of the membrane and of the presence of the mass here, you also create a resonator, and this system is able to resonate with the acoustic wave, just like would be, how do you say, tambour? Tambour, yes. Just like a tam-tam or something. Okay? So, and this system was able to show some resonating behavior with an incoming wave, and it is very useful for example, for the sake of acoustic insulation, where when you want to stop a wave at a given frequency, you can use this type of system, and they were able to stop large frequencies acoustic waves. Okay. So now, what is our experimental strategy? So our experimental strategy is trying to make these metamaterials using other strategy, because I forgot to say that all this strategy here, these three examples, these materials were handmade. These are mechanical realization. They take one ball, they put it in one sphere, and so on. Okay, so this is a handmade material. And of course, if you want to do something, for example, at an industrial scale, or if you want to apply it to make objects of different shape and so on, this is not convenient to work like this. And also the large, here you see the large value of the core here induces very low value of the frequency. So you are here in the low frequency range, and if you want to go to the high frequency range, which is very interesting for the sake of applications like echography or focus of the problem of focusing acoustic waves and so on, you need to work with a very large, much larger frequency. So our approach tends to make metamaterials from fluid phases, and for this we're going to try to make some core shell objects which are inspired from the work of these people here, which have made this particle. What is our aim is to downsize this system, to be able to work in fluid phases, to use colloidal science to make the material, and to attain larger value of the frequency. Okay? So we focus I focus on this type of material first, and you see this is a case of dipolar resonance, where you have the material, the center of mass of these little beads will oscillate, so it means that we are in the first situation that I showed you here. This is the top here, the top drawing here. It means that the center of gravity of this little inclusion will move in space and time as a function of the incoming wave. Okay. So for this, we are going to use, try to make some core shell objects, and this core shell object will be constituted of a small hard core, a soft shell around this core, and then it will be embedded into a solid matrix. Okay? And for this matrix, so for the core, the first choice that we have been doing is where we are going to use polymer particles, and we're going to put this polymer particle into a soft shell which will be made of a physical gel. Yes, this red circle should be on physical gel, I'm sorry. Okay, and so for the core we're going to use PMMA particles. These are polymer particles, which will be in the range of 80 to 100 micrometers. And for the gel, we're going to use hydrogel, which is agarose hydrogel, which is a gel that is very used by the people who work with biology, because this is very simple to prepare. You just mix this powder with water, and you have a system in which which presents a fluid phase at high temperature and a gel phase at low temperature. So by playing with the temperature, you are able to tune the system going like fluid at high temperature. Okay, and what we first need to do to the PMMA particle into the fluid phase of the gel at high temperature. Okay, and what is that? Wait, sorry. Just to show you the rheological property of the gel. So the gel is elastic, so it means that I don't know if you are familiar with rheology. So if you look at a gel has a viscoelastic property, so it means that when you apply a force into this gel, some part of the force is restored to the people who has is restored to the deformation, okay, and some part is dissipated into the material. So the elastic part here is relative to the value of this elastic modulus G prime, okay, and the viscous part is related to the value of the viscous modulus, that is J double prime. So here is a curve of the evolution of these values as a function of the frequency, and we have been able to make some measurements in the high frequency range, and also in the high frequency range we see that we have a material that is more elastic than viscous because the G prime is larger than G double prime, okay? So it into this shell is indeed an elastic material, even at the acoustic frequencies that we are going to look at now. Okay. So for the shell fabrication, now we have chosen the material. Now we want to assemble the thing. It means that we want to make some little objects which are made of a polymer core surrounded by the gel phase, and this we want to be embedded into a hard matrix. So what kind of technique are we going to use? There are many available technique. Here you see emulsion polymerization and so on. And we're going to focus on microfluidic technique. These techniques are able to produce very monodisperse and very regular objects of different geometry. So these are some pictures of some microfluidic device. I don't know if have you ever heard of this microfluidic techniques? You know what microfluidic is? Microfluidic is a technique that allows to manipulate fluid at either the micron or even the nanoscale. So this is a technique in which you mix fluid together in a small channel that can be performed either with glass capillaries on the right. With this technique here you can go down to some typically 100 microns, so you can make channel with 100 microns, and in this channel you can flow some fluids inside, okay? And I'll show you how this can be used to make a new object, to make complicated geometry of objects. And on the left you also have a technology that is microfluidic but using PDMS, which is a polydimethyl siloxane, which is a silicone, okay? And with this system, you can make also some small channels, and you can manipulate the fluid inside the channel. So we have made this following setup. So let me explain. This is glass capillary tubes. Okay. So here, this is a schematic of what we've been doing. In fact, you see the first capillary that is on the left, okay, is smaller, is a round capillary. It's a circular capillary, okay. And if you take this circular capillary and that you put it into a larger capillary with a square section, okay, maybe I can make a drawing on the board. I'm sorry for the in the room. Okay, so this is a section of the external capillary, and this is the section of the internal capillary. Okay, so if I draw it in perspective like this, I'm sorry, I'm not very good at drawing things, but you can have a first fluid coming into this circular capillary, and you can have another fluid in the between these two capillaries here. Okay, so this is what is schematized here on the side. You have the flow of PMMA particle contained into the gel at high temperature, okay, and you push that into the capillary tube, and here in the other capillary you have a co-flow, okay, so you have another flow here of another phase, and in that case this is a silicone oil, okay, so you have here some PMMA particle into the liquid gel phase, which is pushed into the phase which is made of silicone oil. The phase of silicone oil is called the carrying phase, okay, and the phase containing the droplet is the one that will be encapsulated like this, okay. So I can encapsulate little particles into larger silicone droplets, and of course the number of objects that I will put in every droplet here will depend on the concentration, on the number of droplets of particles that I introduce into the system, and on the difference of speed between the speed of the flow that is in the inner capillary and the speed of the flow that is in the other capillary. Okay. So you see, these are some pictures here down at the bottom of the slide. You have some pictures of the object that we are able to make when we, after having found the good condition for the concentration of particle, the flow inside the inner capillary and the flow inside the outer capillary. Okay? And this here, okay, this is a schematic of the experimental setup. So let me go back here first. So you see when you want to push containing the droplets, containing the PMMA particle inside the silicone oil phase, you want it to be fluid, okay? Otherwise you cannot push it through the capillary tube. So it should not be in the gel phase. So that's why we maintain this part of the setup at high temperature above the gel-liquid transition. Once we have encapsulated the particle inside this fluid phase, we decrease the temperature so that the shell becomes coelastic solid. Okay? And we end up with small particles of PMMA which are embedded into a gel phase, and these particles are completely can be into a polymer material that we can or UV procedure or whatever. Okay, and this way we can make some objects of this type of with this type of property. Okay. So this here this is the experimental setup that we've been using. Well, there's nothing really to comment on that. We do that under a microscope because the particles, you see, the particles about 100 microns, so you cannot see it only with your eyes. You need to use a microscope. And okay, so this is a picture of the chip, and here you need to have some heating tapes just to maintain the temperature at the right value. And you have also some apparatus here. This is a red thing here that is what we call a syringe pusher, okay, that will apply a given flow to the fluid inside the capillary tubes. Okay, and after that you have a cool down zone. Well, this is here you have the tube that you roll over some piece of metal that is maintained at a low temperature, just to decrease the temperature to make the gel phase. Okay. And these are again some pictures of the encapsulation. You have accidents. You don't have, for example, in this picture, you don't have a particle here. Okay. One particle each droplet. Okay. Of course, this would be nicer to show you a film, a video, just the right idea. And with this procedure, we are able to produce some material with a particle inside, a larger particle containing the gel phase. Okay. Okay. Another technique that is used to make this type of object, still microfluidic, use what we call a three-step setup. So in of the system, I mean, from the experimental point of view, you we don't inject solid particles. We inject a liquid that will be further polymerized inside the setup. Okay. So in that case, we incorporate a first drop of what is called acrylate EG solution. Okay, and it is an aqueous polymer, aginate. Salt. By applying UV to the system. Okay, and this way also you see we have a 3 steps setup, 1, 2, 3 phase. Okay, and we are able to make some core shell material with a given size and a given value of the size of the shell. And this technique, using this technique, we were also able to produce. So you have some pictures of the setup here, of the setup where it is working. So we are using a liquid inside. With respect to the size of the whole object like this. Okay. And okay. And with this setup, we will to produce the object that you have here. Okay. So this is a 600 micrometer scale here. So you see that the objects are about 0.6 millimeter. Okay. And inside you have a small droplet of the alginate polymerized particle. Okay. So we were able to produce this type of object, but you see one experimental problem is that the core is not always centered at the middle of the particle. Okay. And histogram of the evolution of this decentering as a function that you have in the system. Okay, now how can we make a material with that, and can we try to use this system as a metamaterial? So for this we have used a model that allows us to calculate the value of the resonance frequency as a function of the size of the object. So here is the plot, the calculation that has been made by Liu and co-workers. So what they do consider is just they have exactly in phase with the incoming wave. Okay? If you do this calculation, you show that, so here, the right drawing is the big U speed of the incoming wave, and little u is the displacement of the sphere. Okay? So when is moving in phase coming wave, frequency, so it means that the motion is completely in phase with the incoming wave. Just after, so it means that the motion is in phase with the incoming wave. And here on the left, in terms of the effective density of the material, okay? So when you are just after the resonance frequency, you have a window of frequency in which this effective density is negative. Okay, and is that, so we have been able to calculate the resonance frequency as a function of the core radius and the resonance frequency as a function of the ratio of the shell divided by the core radius. And you see that the larger the core radius, the smaller the resonance frequency. And it's the same for the thickness of the shell. Here you have a plot of the resonance frequency as a function of the value of the elastic modulus of the shell. Okay, so this resonance frequency is a function of the dimension of the object and also on the physical properties of the materials that constitute the core and the shell of the sample. The problem is that if you want to see something experimentally, because we are experimentalists, we want to have something that is possible to measure, we need density will be effective. Okay, so it means that if you have a too small value of delta f here or df here, okay, it means that you would not see anything. Okay, experimentally you're not able to see anything, and so we try to calculate the evolution of this I would say this negative window, okay, as a function of the different value of the system. So we see that this width of the negative window is independent of the core radius and is independent of the value of G prime. Okay? But a problem is that this value of the window, the negative window, is strongly, very strongly dependent, you see, on the ratio of the shell thickness divided by the core radius. Okay, I'm sorry, maybe I should have told you here. B is the radius of the whole object, where A is the radius of the inner core of the material. Okay, so B minus A is the thickness of the shell, and A is the radius of the core. So, and also this negative window is a decreasing function, vanishes when the density of the core is equal to the density of the shell. So this is our problem at the moment, because we have been working with a polymer system in which the inner density of the polymer core is 1.2 times larger only than density of the shell. So we have decided to go to another system, and I will just show you some results, and I will finish with that. So here, to circumvent this problem, we have decided to make some core particles with a very high density alloy. And to be able to still be able to use microfluidic, we have been using and that has a very large density of 9 grams per centimeter cube. So in that case, the density will be 9 times the one of the carrying phase, okay, of the shell phase. So we would be somewhere, so 9 is about here, okay. So we will be completely out of this vanishing point here, okay. And this will increase the value of the negative window. Okay. So we are at the stage of the problem where we are making the small droplet. So we need to work on the microfluidic of this type of system, which is a fused alloy that is dispersed into a liquid phase. So it's not so easy to do. So you see, we are working on the different pressure. The pressure that is applied on the alloy will give a given flow to the liquid alloy, and here the pressure on the external oil will give a given flow to the external oil. And this is what has been done here. This is applied on the external phase, so it is on the liquid phase that is between the droplet here, and in the internal phase that is the pressure that is applied to the flow of the alloy here. And by playing with these two values, we are able to make different objects, which are droplets, what we call plugs. These are little elongated droplets, or jets. These are things like that. You see very irregular things. And once we have chosen the right regime, it means once we are in the right regime of flow, we can decrease the temperature and go back to the solid phase of the inner particles, and this way we were able to make these very regular circular beads, spherical beads of the very dense alloy. So now we are at this stage where we try to encapsulate this alloy into an elastic shell in order to achieve the properties of the material we want to have. Okay. So I'm sorry there is no acoustic measurements yet because we have not finished to construct. This was just the idea to give you. This was just to give you the idea of what we are doing, what is the aim, and what are the experimental techniques that can be applied. But you see that with this type of approach, we are able to really downsize the materials that was used by Liu and co-workers that I showed you at the beginning of this talk, when I talked about this. Sorry, this is a bit long. Yeah. So this is this transparency. So we are able now to go towards the fabrication like this, and the interest using fluid phase. So since we are using fluid, we are able to make materials with a given shape of the materials and so on. Okay. And so with this, I will finish with my presentation, and thank you very much, and I'll be very happy to answer any question. So I don't know if you have any questions. With the fluid phase, so the application is that you see, yes, I can show you. Frequency, okay. So it means that, for example, if you are able to make a material with a core radius of, say, 10 microns, then you are able to work with frequency of around 10 to the 4th hertz, and these frequencies that are used in echography. Okay, so you can example, try to focus. I don't know if you've heard of also medical techniques where they try to destroy some specific places inside your body. And the problem is that at the moment they are not able to focus very precisely the position of the position of the wave. Okay, so this would be an example of using this type of material would be able to focus wave on very specific parts of the body. Sorry? Yes. And also told you that if you send a wave that is exact. If you send a wave that is exactly at the resonance frequency, then the wave is dissipated inside the material, and the wave that will be transmitted through the material will not contain this frequency anymore. So this is just like you make a filter, okay? This is just like if you had a filter, and also you can work in situation where the wave will be at the given frequency will be reflected, selectively reflected by the material, so you get rid of all the other frequency but this resonance frequency. Okay? So there are many applications. Don't know. Are there any questions in the other sites? I don't see that much people. Doesn't matter.
Mérida, ¿tienes pregunta, Mérida?
Okay. Okay.
Mérida, ¿tienes alguna pregunta? Ya que eres la única que veo por ahí conectada.
No, ninguna pregunta. Lo que pasa es que casi no se oye. Debe ser por eso que en las otras sedes se fueron. Se escucha muy feo.
Ah ouais, d'accord. Elle dit qu'elle n'a pas bien entendu, c'est ça? Ah oui. Ok. Okay, you have any other questions? No? Yes? Sorry? The shell. Yes. The shell. Okay, you can make, I showed two examples. Okay. In the first example that I showed you, the shell was made with agarose dissolved in water. Okay. So in the first example, this here, this is the agarose gel, okay, which is fluid at large temperature and which is solid at low temperature. Okay. Whereas in the second example that I showed you here, polymer solution here, this creates some connection between the chain, and this turns the polymer solution into a gel solution. Okay, and then after that, the second step here is the UV irradiation of the system that will polymerize the core. Okay, the ions that are solubilized in the oil, and then you have a polymerization of the core through the UV irradiation. Whereas in the first case, the polymerization there was no polymerization. It's a gelification process, and this is going from fluid to gel phase of the fluid of the capillary tube. Okay.
Thank you. Okay. So I don't know if you have followed before some, probably yes, some lectures concerning carbon and the lectures of Eric Anglare, and maybe in Caracas there was also a lecture made by Vincent Jourdain concerning the different synthesis of carbon nanotubes and carbon forms. So today I would like to make a short, I will try to be short because it's late, a short talk concerning an example of application, how you can use carbon nanotube to make new, in this case, composites. And one of the goals we aim is the reinforcement of mechanical properties. Okay, so this work has been done in our laboratory with all these people. Many of them are PhD students, of course. They are working hard. And as an introduction, I would like to explain you why we want to make fibers, why it's interesting to process material into. So it's interesting to process material into fibers because fibers are of practical use. First of all, it's easy to handle, and structuration of it's easy to understand. And when a compound, I mean matter, is in a fiber, you will very often have orientation. Imagine a polymer to a fiber form, it will be orientated. But not only that, also when you process matter into fiber, you will very often have a thin diameter, very thin diameter, and when you decrease the diameter of a material, you decrease the size of the initial microfractures. They will break because you have microfractures inside. This is an old experiment made by Griffith to make fibers made of these fibers. And when he decreased the size of these fibers, he realized that the strength of this fiber was exponentially increasing with the diminishing of the size of the fiber. Okay, so making fibers can lead to enhance mechanical properties. This is one of the reasons why we were interested in this form. So you have synthetic fibers. And most of them, of course, they are all synthetic fibers. And most of these synthetic fibers are made of a unique constituent, a single polymer, for example, a pure polymer. They have been developed until several tens of years. And of course, because of these developments, they have optimal performances. This is the example of Kevlar. Kevlar is pure polyaramide fiber. The polymer is very well crystallized and aligned. And this is the reason why Kevlar has high performances. Maybe you know that Kevlar is widely used for protection because it can absorb a lot of energy. This is a material that can absorb a lot of energy. But nature is much stronger than we can do because you can find in nature some natural fibers which have been developed until several millions, even hundreds of million years, like spider silk. And spider silk exhibit an equal energy absorption. This is one of the main use of spider. So it's one of the main aim of this material. And if you look inside Spider Sync, you will see that it's a very interesting structure in which you have very well crystallized domain of proteins which are embedded in the middle of amorphous protein. And in some way, it's a kind of nanocomposite structure, okay, with small crystal parts here and around a kind of matrix of amorphous polymer, amorphous protein in this case. So I think that we can take lessons from this, and having a look to that, we believe that it can be interesting to try to make nano-composite fibers using nanomaterials. Because we need synthetic fibers, of course, with better properties and also new functionalities. So nanomaterials can be a very interesting way to make this new type of fibers. So we need synthetic fibers with new functionalities. Just to give you an idea of the type of new fibers that we aim, you can imagine fibers to make textiles, of course, textiles to make sensors for communication, heating textiles, actuators. More generally, we need light textiles with high mechanical properties, for example, to make bulletproof vests, but not only, many types of clothes for clean rooms, antibacterial clothes, conductive textile. Well, that in this domain, in this many possible applications. So, nanocomponents with nanomaterials, of course, carbon nanotubes can be very good candidates to make nanocomposite fibers. So you all know that there are two types of carbon nanotubes, single wall and multi-wall carbon nanotubes. You probably all know also that they have remarkable properties. First of all, a strong anisometry with small diameters at the nanometer scale and very long, very high lengths. They exhibit very interesting mechanical properties, a high Young modulus, a very high strength. They have good electrical properties. The density is very, very small. And of course, they have suitable dimensions to be incorporated into fibers and to take advantage of these very nice properties. Okay, this is for good news. Another good news is also that carbon nanotubes cannot be anymore considered as a lab curiosity. Now the mass production is in progress, and we have been working in our group with the Arkema group, which is able to produce carbon nanotubes at high rates, high yields. So of course it's very important to aim the composite market. But the research challenges are, there are still many challenges to try to process these carbon nanotubes. Why? Because the raw powder that you see here, when you look inside this raw powder, you will see that the nanotubes are completely entangled, disordered. They look like this, so they are very far from the ideal. And the aim is to synthesize the macroscopic composite fibers with these nanotubes, keeping most of their exceptional properties. So we have to be able to control the dispersion of the nanotube, to control their organization, and to understand how the nanotubes are interacting with the matrix that we will use. Okay? So, just to say a word, I don't know if you are familiar with mechanical tests, with mechanical measurement. How do we make a mechanical measurement on a fiber, like typically with the size of your hair? Okay, so we are not at the nanotube scale, of course. You imagine a macroscopic form. Here you have this fiber, and you put it inside a setup, a seed load experiment setup. So you stretch this fiber, you pull these two parts of the measurement setup, you stretch the fiber, and then you measure the force which is necessary to stretch the fiber and finally to break it. And this is a typical stress-strain experiment. Here is the stress. The stress is the force that you need divided by the surface, the section of the fiber. Okay? Of course, the strain is the deformation rate. So, typically, this is the kind of results that you will get this kind of curve. And so, you can extract different values, results from this curve. The first values that you can extract is the Young modulus, E, find the rigidity of the materials, how rigid. And this is the slope of the first part of the curve, okay? In the elastic regime, this is the elastic regime, where the deformation that you apply is reversible, completely reversible. Then after, you have the plastic regime here. Here, at this point, the deformation is completely irreversible, okay? And here you have the maximal, the failure stress, the maximum breaking force that the material can stand. And corresponding to this value, which is what is called the tensile strength, you have the failure strain, which is, as you can easily understand, the maximum strain deformation that the fiber can stand also. Okay? These three Young modulus, tensile strength, and failure strain are the main mechanical features that you want to get when you measure, when you make a tensile load experiment on your material. And it characterizes the mechanical of your material. So, what are the requirements for an efficient mechanical reinforcement when you put, imagine, small rods like nanotubes in a polymer matrix? Okay, so these small rods are indexed here by if like fiber. So don't mix here in this case the if for fiber term, the small nanotubes in the polymer matrix. Okay. So, we can follow simply what is called the rule of mixture. What happens when you put little fibers like nanotubes inside a polymer matrix? So this is the Young modulus, which defines the rigidity of the final material, the composite. You see that this Young modulus is a combination between the Young modulus of your little fibers, of the nanotubes, and you know that this Young modulus is very high, and the Young modulus EM of the matrix, of the polymer, which is much smaller generally. So this is a combination of two. Here, phi if is the fraction of nanotubes that you will put. And these two parameters, eta 0 and eta f, I'm going to explain what they mean. Eta f, forget this, just keep in mind that the effective length coefficient is something that says that the nanotube have to be as long as possible to induce a good reinforcement. Okay? This coefficient goes to 1 if the aspect ratio of nanotubes is high, is very high. Okay? Eta 0 is the orange coefficient. It varies from 1/6 to 1. 1/6 if the nanotubes are completely disoriented, and 1 if they are perfectly oriented within the composite. So that to obtain a higher a Young modulus as high as possible for the composite, you have to get a high concentration of nanotubes, replace fibers by nanotubes, okay, as high as possible. A high fiber aspect ratio, so nanotubes can be good candidates for that. Alignment in order to increase as much as possible this orientation coefficient. And also something that which doesn't appear here in this formula but which is intrinsic is a perfect stress transfer. That means that the adhesion between the nanotubes and the polymer matrix has to be as best as possible. Okay? When you pull on the composite, you pull on the polymer of the matrix, but you also pull on the nanotubes. And the reinforcement will be the best if you pull as much as possible on the nanotubes themselves. And to do this, the stress transfer between the polymer and the nanotubes has to be as best as possible. It's okay? So, to do this perfect stress transfer, you have to play to understand very well how the interface between the nanotubes and the matrix is working, and sometimes to play with chemistry, of course, with the surface of nanotubes, with the polymers that you choose, and so on. Okay, how do we process macroscopic fibers? There are various approaches to fabricate nanotube fibers. Some approaches are based on already known processes which have been developed from several years. It concerns the addition of nanotubes to already known polymer fibers. These are robust processes, but very often you cannot get a high concentration of nanotubes. You have less than 10% of nanotubes in such fibers. You can also find more recent processes like direct or quasi-direct carbon nanotube spinning, or in which you will get high nanotube volume fraction. And in our lab, we have proposed in 2000 a coagulation spinning, a new coagulation spinning. So because time is going, maybe I will be quicker to describe this. Among well-known processes, you find what is called melt spinning. It's a very industrial and well-known process in which you will mix the polymer, a few percent of nanotube, and you will melt this mixing. And generally, you cannot put a lot of nanotubes inside because it becomes very viscous when you put nanotubes, and it's not possible to process it. And this mix of polymer and nanotubes, melt polymer and nanotubes, you extrude it like this, and you can make fibers with this process. But as I told, it's fast, robust, but you cannot increase the quantity of nanotubes. Okay, so you have limitations. So with this kind of well-known processes, you can make a lot of fibers. I won't go into details, but generally you aim good Young modulus, but not so good. I mean, it's not always the young modulus that you aim are not so high, and the strengths are not so bad, but not so high also. So I skip to the next one. You can find more recent processes to perform nanotube fibers, like direct spinning of carbon nanotubes. And with this kind of processes, you can get 100% nanotube fibers. These processes are always working like this. This is the furnace in which you produce the nanotubes, okay? And you directly pull the nanotubes at the exit of the furnace, and then you can pull several nanotubes together and make 100% carbon nanotube fiber like these ones. These are nice carbon nanotube fiber composed of only carbon nanotubes, very well aligned. This is the reason why you have high electrical conductivities, high strength, and high strain to failure also. This is not really scalable. It's not easy to upscale this kind of process. Another coagulation spinning process which has been developed in Rice University in Texas. They solubilize carbon nanotube in super acids, and then they inject this solution in acetone, and they induce the coagulation of nanotubes. I won't go into details, but just remember that it's in super acids and it's of very difficult handling, of course. It's not easy to handle. But they are very nice, also very good carbon nanotube fiber. Let's come to the coagulation spinning that we proposed in our lab. What do we do? So we take the carbon nanotube powder. Okay. The first step is the dispersion of this carbon nanotube powder into water and to disperse carbon nanotube into water, because nanotubes are insoluble in almost any solvent, they are insoluble, you have to use surfactants. So we use surfactants. These surfactants are absorbed on the surface on the nanotubes, and they induce the dispersion of nanotube into water. Then we take this dispersion and we inject this dispersion using this syringe here that you see into the coagulating bath. In this bath, what do we have? We have water and a coagulating polymer. This is polyvinyl alcohol. What happens when we do that? So I have to take. This is a video, so I have to. Yes, we can. Okay. Hop. Okay. So when you inject a dispersion inside this coagulating media, you observe the spontaneous formation of a fiber, as you can see here. So what happens when the nanotubes arrive in contact with the coagulating fluid? The polymer which is inside this fluid will replace the surfactant on the surface of the nanotube, and then it will bridge the chain, which are rather long, will bridge the nanotube together like this, like what you see here. And then you can make a macroscopic fiber in which you have carbon nanotubes embedded in a polymer matrix. Okay? So it's a very simple coagulation process using water, using a simple polymer, and which has been, we have patented this in 2000. So we worked during several years with this small setup, and because the properties of the fibers we obtain, I will show you this after, are very interesting, we decided to upscale this process to make something more continuous. If you want to make kilometers of fibers, of course, setup is not suitable, of course, you can understand this. Yes. So you make fibers like this. The size of this fiber is typically, the diameter is in between, let's say, 30 micrometers and 100 micrometers. So as I told you, we upscale this process. So here you have the dispersion. You inject it in a coagulating bath as before, but it's continuous, it's a linear process now. You have here a washing bath, a bobbin, and normally there is also a, yes, it should have begun alone. I think it's not working. Okay, forget it. And when you do this, you see that it's possible to, do you see the fiber here? It's possible to make continuously a fiber and meters of fiber continuously and to get bobbins of this fiber. With this scaled up process, it will be easier after to have high quantities of fibers and then to make textiles, to make tests for some applications, of course. So if you look inside these fibers, what do you see? You see these carbon nanotubes that you can guess here, okay? And they are not so badly aligned, okay? They are not very, when you measure the alignment, it's not so good. But here it is not so bad. And these carbon nanotubes are embedded in the polymer matrix that you see all around. So it's an aligned, it's a nanocomposite structure with a large amount of interface. The polymer is confined in between the nanotubes. And we expect so the properties of this fiber to be different from conventional polymer because of the presence of carbon nanotubes. What are the mechanical properties? This is a tensile stress experiment, as I've shown before, okay? And this is the behavior of our fiber. So here you have the slope of the elastic regime. The elastic regime is very short. And then you have a very, 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 very long plastic regime. And here you see the failure, the breaking of the fiber at this point. If you calculate the Young modulus, it's 5 GPa. Just to give you an idea, it's not so bad. But pure carbon fibers are much better, 2 orders of magnitude better. So these carbon fibers are very interesting, but they are brittle. They break very easily. The tensile strength is not so bad also, but once again you can find polymer fibers with better tensile strength, and it's the same for strain to failure. In fact, this is a combination of the 3 properties which is interesting, and the combination of these 3 properties is the area under the curve. And the area under the curve is what we call the energy absorption, the quantity of energy that the fiber can take before breaking, okay? And this energy absorption is very high, it's 900 joule per gram, to be compared with Kevlar, which is an industrial synthetic fibers, which is used for this ability to absorb energy. So we are much higher, and also much higher than spider silk. But in our case, the price to pay is that the deformation rate is very high also. So the fiber will deform a lot before breaking, and this is not always suitable. Just to explain you a way to understand what is energy absorption. It's not always easy to understand exactly what it is. Let's take the example of spider silk. I said it has been made by Mother Nature to stop projectiles with a high energy absorption, 160 joule per gram. When a material like spider silk can stop 1 kilogram of spider silk can stop 300 kilogram projectile launched at 100 kilometers per hour. This is a way to understand what is this value of energy absorption. So a motorcycle with the man on it can be stopped. But you can imagine that to make 1 kilogram of spider silk, it's not easy because of the density of spider silk. Just to compare, 1 kilogram of Kevlar can stop 90 kilograms, and 1 kilogram of steel can stop 50 kilograms. So spider silk is a very performing material. But you've seen that our nanotube fibers are even higher than this. Okay? So, as I said, it's a high value of energy absorption, but it's not suitable for many applications. Imagine if you want to make a bulletproof vest with our fibers, you don't want this rate of deformation, of course, because, well, the absorption that will be absorbed will be high, but the guy wearing the bulletproof vest will be dead also due to the deformation, okay? So we have to be able to decrease this deformation rate, and to do this, we made hot stretching of the fiber. What is hot stretching? We put the fiber inside the furnace, and then we stretch it while heating it at the same time. And then we heat it, we stretch it at the same time, and then we stop heating. And we keep this fiber under stretching, and we cool it down under stretching, keeping the force, keeping the stress on the fiber, okay? And this is something which is widely done in industry, in textile industry too, to improve the polymer properties. And when we do this, we change the structure, completely change the structure of the fiber. Don't read anything, but just to tell you, when we measure the orientation of the nanotubes inside the fiber before this treatment and after this treatment, what we see is a strong improve of the nanotube orientation. This is the value of orientation of a raw fiber. It's oriented at plus or minus 26 degrees if you compare it to the axis of the fiber. So there is a large distribution, and once you have stretched the fiber, hot stretched the fiber, you improve this orientation a lot. So they are much better aligned, the carbon nanotubes. It's also the same for the PVA chain, the polymer chain around, okay? And we also see that the crystallization of the polymer is improved by the heating process also. And this led to completely different mechanical properties than before. This is the raw fiber that I've shown before, and this is the same fiber but after the hot treatment. And you see that the mechanical curve is absolutely different. We change the Young modulus, we change the strength, we change the deformation rate, which is much smaller now. And of course, we also decrease the energy absorption, but it's still very interesting. It's 60 joules per gram with 11% of strain. And now, this material is of great interest to make protection for protection application, like bullet professor or bumper or whatever you can imagine. Okay. Just to compare with other type of fibers, you see that we have very high energy absorption. This is the carbon nanotube, the raw carbon nanotube fiber before treatment, the same after treatment. So, of course, here it's smaller than spider silk, but it's still higher than Kevlar. So, I think it's very interesting. Just to see carbon fiber. The best carbon fiber made by Torre have very young high modulus, but very low deformation rates. This is the reason why they are not flexible. They are very brittle. And the energy absorption is also very small. So, they are not suitable for protection application. For some other application, yes, but not these ones. Okay, I don't know how much time do I have. Do you know, I did look to my watch, so I time or not. Ça fait 5 minutes. So if I only have 5 minutes, I'm sorry, but I have to skip some slides concerning the stress transfer and Raman measurements to measure this stress transfer. So I'm sorry, I skip this. I just want to finish with a very funny effect that we see on our fiber, which is called the shape memory effect. Are you familiar with shape memory materials? Do you know what it is or not? Shape memory effect. I can explain this very quickly. It's a well-known effect in polymers and metallic alloys. How can I explain this in polymer? Imagine that this is a polymer. Sorry, I'm trying to find the laser. Okay. Imagine that this is a polymer. So in many polymers you will have amorphous chains, and you also find some little crystallites, okay, of the same polymer, of course. This is typically semi-amorphous, or we call semi-amorphous polymers, or semi-crystalline polymers. It's the same, semi-amorphous. Polymers, when you hot stretch a polymer like this one, okay, so you heat it, you stretch it. So basically what you do, you align the crystallites of polymers and the chains within the polymer. Then if you cool down this polymer, keeping the stress, okay, you will have this, an aligned structure like the fibers, like what we do with the fibers. Then if you reheat the polymer, the chain want to go back to their initial shape, and you will observe a global contraction of the polymer, okay? The polymer stores energy during the hot stretching process, and it gives back this energy when you heat the polymer again. And it's a very well-known effect. And in polymers, the value of the force, what we call the stress recovery, when the polymer recovers its shape, it develops a force, a stress, and the value of this stress recovery is 2 megapascal for conventional polymer. So it's a little force, it's not a big force, okay? But the strain is high. The strain is high, but the force is very small. The stress is very small. However, small, it's widely used in packaging, for heat shrink tubing. You know what is heat shrink tubing? You have polymer tubes around the electric cables. And these polymers are, they stretch the cable, and they use this polymer shape memory effect to fabricate this cable with the polymer tubes around. So for heat shrink tubing, for foams and so on, there are various applications. Because the stress recovery is very small, it's too weak for some application. especially, for example, in aerospace, where they aim deployable, inflatable, foldable structures for aerospace. So we were thinking that our fiber, because the fiber can be outstretched or pre-deformed at up to 800%, a lot of deformation, we believe that this fiber store a lot of energy. And store a lot of energy, maybe it can restore, give back a lot of energy too. And maybe the shape memory effect will be very high. So, indeed, once again, I have two movies to show you. This is only qualitative. No. Okay. So, in the first case, you see our fiber, and then we eat it. And we clearly see the shape. You see the contraction of the fiber and making this small knot here. Okay, strong contraction. And the other funny movie, here you have the fiber. The fiber is attached on at an electrode here, and here you have another electrode, let's say. And we induce heating of this fiber by Joule effect. There is a current, okay, going through the fiber. And just to show you, so at the first moment you don't see anything, and then, clack, you see the contraction, the very strong contraction of the fiber at this moment. So the force seems to be interesting, the stress recovery. So when we measure the stress, this is for fun, we made video for fun, but then we measure the stress recovery with this setup. It's a furnace in which you can stretch the fiber and then measure the forces. It's a tensile load setup. And when we do this, indeed, we have measured stress recovery up to 150 megapascal. Remember, for conventional polymer, it's a few megapascal. So we are much higher, we have much higher effect. And the strain is also very good. And we also observe something very particular that has not been observed to the best of my knowledge before, which is a temperature memory. The maximum of stress recovery that you get at the end, it's at the temperature where you have pre-deformed the fiber. And normally you don't see this in conventional polymer. In conventional polymer, it's always the maximum of stress recovery is always at the TG, the glass transition of the polymer. So I won't insist on that, and I think that I will end with this effect. I want to thank the nanotube group, of course, in Bordeaux, and the collaborator of this work, and you for your attention at this very late time. You are probably very hungry. Okay, I stop here. Do you have questions? No, you are too hungry. Okay. Yeah. 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 It's probably a collaborative effect between the nanotubes and the polymer. The polymer, the shape memory effect comes from the polymer, but because of the presence of nanotube, thanks to the presence of nanotube, we could pre-deform the fiber much higher, much better than if you only have polymer. And so, if you pre-deform it a lot, you store a lot of energy. You've seen 900 joule per gram, and then the effect, the stress recovery is much higher than with a pure polymer because you have stored a much higher quantity of energy. And so this is the reason why you see that it's very strong. It's very strongly comes back. It's the shape recovery of the polymer, but the storing of energy is higher because of the presence of nanotubes. Okay? I don't know if I am clear. Yes, I've skipped this. It was a Raman experiment, but somehow you also store energy because of that. You deform your nanotubes also. Yeah. Yeah. No, no. In the first coagulating bath, which was turning like this, you remember? We inject the nanotubes in water into the polyvinyl alcohol, which they are separated before. Because if you mix the polyvinyl alcohol with the nanotube, then you induce the coagulation. And at the beginning, in the dispersion, you don't want that. You want a very homogeneous dispersion that you bath and induce the coagulation. Okay? Okay, time for lunch or? I don't know, I think there is nobody in Merida or in Caracas. Okay.